Hello everybody and welcome back to the Probability and Statistics Prelim Review in the summer of 2020. We are going over the prelim dated January 2020 and we are on problem 2. So the first thing you should do if you haven't done it already is read the problem. So this is the time to pause the video and read the problem because I don't think you want me reading it to you. Okay, welcome back. So you just read the problem and you realize that this is a problem from the Markov chains class. It involves a continuous time discrete state space Markov chain with a generator matrix and exponential things and maybe some Kolmogorov equations. So in part A, we want to write down the generator matrix and this should be pretty quick. So I think the first thing I'm going to do is just take a moment to identify the states. So state 0 is the state that the machine is working. And state 1 means the machine is in repair. So we were given that if it's in repair, it's going to be there for an exponential amount of time with rate R. So the rate of going from in repair back to working is R. And it's also exponential. And then going the other way, the rate of moving from state 0, from working to failure to state 1, that's the failure rate. And incidentally, even though the problem does not say that there is an exponential amount of time until failure, that is a property of continuous time Markov chains and the fact that the exponential distribution is the only continuous distribution with the lack of memory property. So it is safe for you to say that the lifetime of the machine, or the working phase of the machine, is exponential with rate f. So with that, we're ready to put together our generator matrix. It's typically called Q. It's got a row and column for each state in the state space, and I would recommend leaving the diagonals to the end. So the first entry I'm going to fill in here is the 0, 1 entry. So this is the rate of moving from state 0 to state 1. And so in words, this is the rate of moving from working to being in repair. So this is the rate of like the lifetime being used up. It's the lifetime rate, or F, which is a failure rate. So I'm using the words kind of strange. It's the amount of time until failure. So it's the time of the life of the machine. Okay, and then moving from state 1 to state 0 means we're going from in repair back to working. So this is the time of a repair, and that is exponential with rate R. And I was supposed to be drawing an F in the upper right corner, but I forgot to cross that F. And then because the rows of a generator matrix always add up to 0, we can just fill in the rest. And we are done with part A. Okay. On to part B. What is the probability that after a very long time the machine is working? Very long time. This is like a limit or a long run proportion of time that we are in the working state. So this is, let me write that down, this is a limiting probability or a long run proportion of time in the working state, which is state 0. And in Markov language, what we want here is pi 0, the stationary distribution or limiting distribution for the state 0. So if the first thing that comes to your mind is that you should run down the columns of the matrix and peel those off as coefficients for the pi's, then you are thinking about this the wrong way. You are thinking about the fact that pi as a vector times p has to equal pi. That is the stationary equation, but that only holds if you have a P matrix that does not depend on time, so a discrete time Markov chain. In the continuous time case, where we have a generator matrix, we want to use the fact that pi, the row vector, times q is equal to the 0 vector. So if we write this out, we've got a pi 0, pi 1, and then we've got our q matrix minus f, f, r minus r, and we want this to equal 0, 0. So if you start multiplying out the rows and columns, we get minus f pi 0 plus r pi 1 is 0, and then the other equation is f pi 0 minus r pi 1 equals 0, which is not giving us any additional information. It is just -1 times the first equation. So I've got two unknowns and essentially one equation. So we don't want to forget to use the fact that these pi probabilities have to add up to 1. So I'm going to use one of these equations, say this one, along with this one. I'm going to take this second equation that I circled and lost my pen, and multiply it by r, and then add the equations together, in effect canceling out the term I don't care about with the pi 1. So when I do that, I'll get the first equation here, which is f pi 0 minus r pi 1 is 0. And then I'll get the equation where they sum to 1 multiplied by r. So r pi 0 plus r pi 1 equals r. And then I will add them together. And these guys will cancel. So we have f plus r pi 0 equals r. And we can solve that for pi 0, getting r over f plus r. And we are done with part B. All right, moving along to part C. If the machine is currently working, what is the probability it continues to do so without interruption during the next t units of time? Explain. So in Markov processes, which are always time homogeneous unless stated otherwise, whenever I see the word current, I would think of that as time 0. So this is current time. And so it is working at time 0, which means it's in state 0. And then I want to just fix some t units of time later, and I want the probability that it continues to work without interruption during the next t units of time. So you might think for a moment that you want to compute the probability of going from 0 to 0 in t units of time, but that would be wrong, because that would mean exactly what I said, the probability of going from 0 to 0 in t units of time. And that's not what we want, because we want to make sure we've never changed away from state 0. So this thing I wrote down and crossed out over here could mean that in t units of time, we hit state 1 a dozen times in between, as long as we started and ended at 0. What we really want is, starting in the working state, we want the probability that the lifetime goes on for greater than t units of time. So let me scroll back. I don't know if I named this. I did call it a lifetime before, so I think we're okay. So we want the probability that L for lifetime is greater than t, where L is an exponential random variable with rate f, that failure rate. And again, I'm using that fact that I stated in part A. Even though you weren't given that the failure rate is exponential, for a continuous time Markov chain, the times to transitions are always exponential, because we wouldn't have a Markov process without that lack of memory property. So we just want the tail end of an exponential CDF. And if you know it, go straight for it and write it down. If you can't remember, well, work it out with an integral, or turn this around and maybe you remember the CDF. So this is 1 minus the CDF for that exponential, which is 1 minus e to the minus ft. And we get e to the minus ft, and we are done. All right. Finally, the last part of the problem, part D, if the machine is currently working, so again, I'm going to let current be times 0. What is the probability that it is working t units of time later? And this may allow for it to not work and be repaired, and not work and be repaired once, twice, 100 times. So we just want the probability of going from the working state 0 back to the working state 0 in t units of time. So what we want is what I would call P00 of t. This is the probability you go from 0 to 0 in t units of time. So this is the probability that the chain at time t is 0, given the chain at time 0 is 0. Or you can start at any time and look at t units of time later. And to get this, I will use one of Kolmogorov's equations, either Kolmogorov's forward or backward equation. So I'm going to use the forward equation. It really doesn't matter. Kolmogorov forward equation. And this is the one that says that if you take the matrix filled with transition probabilities over a specific period of time p, that the derivative of that, which is element-wise derivatives with respect to t, is going to be the matrix times the generator matrix. And so if we write out just the ijth entry here, we get that the probability you go from I to j, state I to state j in t units of time, the derivative of that is going to be the sum over all the states k, in this case the states are 0 and 1, of the probability you go from I to k in t units of time times the rate q kj. And if you write that out, this becomes a p, actually, sorry, I don't want to write that out yet. I care about it for a specific I and j, so let me go ahead and write that in. So P00 prime of t, so my I is 0 and my j is 0 and my k is going to run over 0 and 1. And so this is going to be P00 t Q00 plus P01 of t Q10. And I do know the Q's. I'm going to pull that out of the matrix I made for part A. And this is negative F P00t plus R P01 of t. So we need to solve this differential equation for P00 of t. And when you only have two states, I think the easiest thing to do is rewrite. So you're going to see a P00 in here and a P01, and I would rewrite the P01 as 1 minus P00, in this case of t. So when you do that and rearrange things here, you've got P00 prime of t plus F plus R P00 of t equals R. And then to solve this differential equation, if you look at the left side, it almost looks like a derivative with an e. And in fact, you need to multiply through by an integrating factor, e to the f plus r t on both sides. And then you'll see that on the left side, you have the derivative with respect to t of e to the f plus r t P00 t. And on the right, we have what we have. By the way, I should have mentioned at the beginning of this problem, if you're more comfortable with using symbols like lambda and mu here instead of the f and r, by all means do so. Just make sure you make a note of it on your exam that you are using lambda for f and mu for r, or whatever you're doing. Okay, so I'm going to integrate both sides. With respect to t, and because I have a derivative on the left side, I'm just going to get the this guy back. So I'm going to get e to the f plus r times t, p00 t. And on the right side, I'm actually going to do the integral with respect to t. So that'll pull an f plus r out in the denominator. And then I'll get plus a constant. Remember, we're trying to solve for p00 of t, so I'm going to multiply both sides by that e to the negative f plus rt. And I've got p00 of t equals r over f plus r plus c e to the negative f plus r times t. And to finish this off, we want to find c. And so we have an initial condition here. We do know the probability of going from 0 to 0 in 0 units of time. That probability is 1, as it would be for any subscripts here as long as they're the same. The probability of going from 1 to 1 in 0 units of time is 1, because we're not moving, so we're definitely staying where we are and moving from 1 to 1 with probability 1. So using that initial condition, plugging in 0 here, plugging in 0 here and setting this whole thing equal to 1, you will see that c is going to be f over f plus r. And so we can pull it all together, and our final answer is the probability of going from 0 to 0 in t units of time is r over f plus r plus f over f plus r e to the negative f plus r times t. And we are done. So I will see you next time with problem 3. Bye.